This is the second class example problem for conservation of energy in what I'm calling a perfect world. In a perfect world, everything coasts. There's no outside forces like friction or motors or pedaling, and the only force you need to work with is right now gravity. So the question is, is the velocity at a height of 3 meters? So to solve this, I'm going to follow the same steps that I did before. Only this time, when I pick my two locations, I'm going to pick the height of 3 meters instead of the maximum height. So first step was our picking our two locations where we're going to compare the energies. I'm going to start with the hill bottom because that's someplace where I know the height and I know the velocity. And then my second place is given by the question where it says, what is the velocity at a height of 3 meters? So that's going to be a height of 3 meters. And I'm going to put on here, for the sake of comparison, our previous answer when we did the maximum height. So that's what we had on the previous sample problem, just so we can kind of look at it and compare. All right, so let's look at the bottom. At the bottom, I have total energy. So it's a bar that just goes all the way up the graph, real nice and simple. And then I go through and I ask my questions. At the bottom, is it moving at this location? And at the bottom, it is moving. It's moving at 10 meters per second, so I have kinetic energy. Then I ask my next question. At the bottom, is it lower than the other location? And it is. It's the bottom. So I don't write anything there. All the energy is stored in kinetic energy. At a height of 3 meters, total energy is still going to be the same. And then I go through the same questions. At 3 meters, is it above the other location? And it is. Now, in terms of how high to make this bar, I know from the previous problem that the maximum height was 5 meters where it came to a rest. So 3 meters is not quite half, it's a little more than half. So I'm going to make my bar a little more than half. If I don't know the maximum height, just draw a bar. And then the kinetic energy, is it moving at this location? And the answer is yes, because it's not at the maximum height. So that sets up my LOL energy graphs. Nice and simple. Now, to communicate what's going on, I need to write the first equation, which we always do the same type of setup for every problem. We write sigma, which means sum, a capital E for energy, and then the location for subscript. So sum of all the energies at the bottom equals sum of all the energies at 3m, and that's going to be my height. Next step, I need to define what energies I'm looking at. So I'm just looking at KE and PE for right now. So I'm going to write KE and PE equals KE and PE. Then I've got to figure out which of these energies goes away. So if I look at my LOL diagrams or I think about my questions, either way, I know that at the bottom, I'm going through and saying, is it moving at this location? And I said yes. And so that's this kinetic energy. So I'm going to keep it in my equation. Then I said, is it above the other height at this location? And I said no. So I didn't draw a line. So I'm going to get rid of that potential energy. So I'll just draw a line to mark it out to communicate that. And then at 3 meters, is it moving at that location? We think so. So I'll keep that one. And is it above the other location's height? And yes, it is. It's 3 meters above the other location height. So wherever there was a bar on my graph, I'll keep it, or I can just rely on the questions, whichever you're comfortable with. Next step, I'm going to add my formulas for each of the energies that I have. So 1/2 mv squared equals mgh plus 1/2 mv squared. And if you look at this carefully, you can see that in each of the three expressions that are on the page or on the screen, I have a mass. So I can divide the mass out from each expression. So that's what I'm going to do. You can't always do this, but right now in our perfect world setup that what we're calling the perfect world setup, it works great. So 1/2 v squared plus gh or equals gh plus 1/2 v squared. Next step, isolate the unknown, and that's going to be the velocity on the right-hand side. So when I do that, I'm going to move gh to the other side, and then I'm going to multiply both sides by 2 and then square root. And I get an expression that looks something like this. And then I'll enter numbers and units. So remember something about this. When you're putting in the numbers and units, it can get kind of confusing because it looks like I have two V's, and you may be tempted to delete those in the earlier steps, but you cannot because they're actually different numbers. So on the right-hand side, that velocity comes from the height of 3 meters. On the left-hand side, that comes from the bottom. That's 10 meters per second. So they're actually not the same values because they're different locations. If you find this hard to track in your head, then take an extra second or two and put subscripts on it. So maybe I'll put B for the velocity at the bottom and 3m for the velocity at a height of 3m. So my expression will look something like this, and like this. And now I can kind of keep track a little bit easier. It's up to you. When I'm doing things, I usually don't put all these subscripts on it, but if you find it easier to track for yourself, it's only a couple extra seconds and it's a great practice. So now I'm going to put in my numbers and units because I've separated them out and figured out what goes where. And the last step I'm going to go through is I'm going to solve this. And when I solve it, I'm going to get a velocity at a height of 3 meters of 6.42 meters per second.